To wrap up binomial distributions, I want to talk about the mean and standard deviation of these distributions, as well as the normal approximations for the binomial distributions, and we'll do that by going through an example from your book. I'm going to give you the formulas since I'm not there today. The proofs are on page 525. I strongly encourage you to read the rest of Chapter 8, at least the binomial distribution section of Chapter 8 if you haven't already, just to familiarize yourself with these topics. Again, we'll get to geometric distributions next class. So you're going to have these formulas for the mean, or we also know it as the expected value, and that's going to be n times p. Remember that we're talking about these binomial distributions with n observations and p as our probability of success. X is going to be the number of successes, so the expected value of x is just n times p. The standard deviation is under the square root like we normally see it. It's n times p times 1 minus p. Remember that we might also see that 1 minus p as a q. So if you see the square root of n p q, that is the same thing. So again, I encourage you to look at the proofs of why that is true. We want to be careful not to round the mean nor the standard deviation to a whole number. We've talked about this. Even though a decimal might not make sense in context, it will be more accurate in calculations if we use some decimal places here. So we're going to use 4 decimal places for the standard deviation. For the mean, you want to toss a couple in there. It won't be always necessary to go to 4 like it does for the standard deviation, but we'll talk about that more in different problems. So if we look at our first example here, familiar topic, we have the probability that a child has at least one parent with a college degree is 0.6. Now we're going to take a simple random sample of 200 students instead of 6 students like we were before, and we want to know the expected value. So remember, the expected value is the mean of children that have at least one parent with a college degree out of that simple random sample of 200. We also want to know the standard deviation. So this is a binomial distribution, now with 200 observations, a probability of success of 0.6. So the mean of this distribution will be 200 times 0.6. You're not even going to have to do any rounding because it's going to come out to a whole number. Make sure you include some type of unit, so we're talking about kids here. And the standard deviation of this distribution will be the square root of 200 times 0.6 times the probability of failure, so 0.4. That will give you approximately 6.9282 kids. And that's all you need to do for that problem. I also want to mention that these formulas are on your formula cards, and so you do not need to memorize them. You just need to know where they apply. The real good part of today is talking about what happens as n gets large, and that we can use normal approximations for these binomial distributions. You'll see when we work through this example that oftentimes the normal approximations are a little bit more work than the binomial distributions themselves, but as we continue to move throughout the course, you'll see why it will be helpful to be able to use these approximations as well. So let's suppose we have a binomial distribution with parameters n and p for some random binomial variable x. If these conditions are satisfied, so if we take n times p and it's greater than or equal to 10, and then if we take n times q, or the complement of p, that's also greater than or equal to 10, if both of these things are true, then we can use the normal approximation for the new distribution with the mean and standard deviation as they are defined above. You do need to show that you've actually checked these criteria before you go ahead and do any of these calculations. And I'm going to show you that by looking at problem 822 from your text. So I'd like you to go ahead, open up your books, read that example, and we'll get started on it in just a second here. So at this point, you should have read problem 8.22. If you haven't, pause the video so you can do that. I'm hoping that you understand that we're going to define our random variable x to be the number of home runs that McGuire hits, and that this is a binomial distribution with our fixed number of observations, 509, and then our probability of success of 0.116, since this probability of hitting a home run is 11.6%. First thing we're going to do is find the means and expected values, similar to how we did on the other page. So our mean is going to be 509 times 0.116, and we'll get 59.044 home runs. Make sure you're describing the variables. For our standard deviation, we'll take the square root of 509 times 0.116 times whatever 1 minus 11.6% is, so I think that's 0.884. That should look like a parenthesis over there. So all that pops under the square root, and we will get about 7.2246 home runs. That looks like hours. Home runs. Okay. So the probability that we're interested in this case, is the probability that he hits more than 70 home runs. So the probability that x is greater than 70. And we're going to use the normal approximation to find this probability. Then I'm going to show you that it would be a similar answer if you use the CDF function on your calculator. So in order to use the normal approximations, the first thing we have to do is check the conditions. So in each case, you're going to take n times p, show that that's greater than or equal to 10, and then n times q, or 1 minus p, show that that's greater than or equal to 10. You have to physically show me this on your work, and if both of those are satisfied, then we can use the new distribution. So we really have already found n times p. That's about 59, our expected value, and so that is in fact greater than or equal to 10. We're good to go. And then if we take n times q, so that would be 509 times 0.844, we will get 450, or something very close to it. It's certainly greater than or equal to 10, so we can go ahead and check off that condition as well. So now we can think about this binomial distribution as a normal distribution with mean equal to 59.044, however it was calculated above, and a standard deviation of 7.2246 home runs, again, what we calculated up here. Once you have a normal distribution with a given mean and standard deviation, you're just going to apply familiar strategies in order to find our probability of interest. So I'm just going to go ahead here and clear my screen so that I can show you how that should look. Alright, I'm going to make a small correction here. I just reread the problem and it looks like we want to know the probability that he will hit 70 or more. So this should actually be the probability that x is greater than or equal to 70. I didn't have the or equal to sign in before. It's not going to make a difference for our normal calculations, but when we check it against the binomial CDF, it will make a small difference. So this should look familiar to you. I've rewritten our normal distribution parameters, our mean and standard deviation calculated from the formulas given. I've drawn a normal curve showing the mean in the middle where 70 falls, and then we want the area above 70. This is our probability statement, and as we've practiced, we are going to go ahead and start working with our z-scores, making sure that notationally everything matches up. So we're going to find the probability that our z-score is greater than or equal to 70 minus our mean divided by our standard deviation. You're going to calculate that to 2 decimal places. Z-scores are always 2 decimal places. And in this case, It looks like that's going to give us 1.52. And so you'll look up 1.52 in your table, and you'll find that the area below that is 0.935. So in order to find the area above, or the probability that Z is greater than or equal to 1.52, we'll take 1 minus 0.9357 to give us a final probability of 0.0643. You're going to give a statement that sounds something like this. There's approximately a 6.43% chance that McGuire would hit 70 or more home runs in 1998 based on his previous season. So that does seem fairly unusual. Now, as promised, I just want to show you what would happen if you were to use a binomial CDF function to calculate this. Might be a little bit easier. So in this case, we have our same probability statement, x is greater than or equal to 70. So I'm going to use the CDF function. Thinking of this, if I just think about the numbers surrounding 70, 68, 69, 70, 71, and so forth and so on either side. Greater than or equal to 70 is going to be this section of my distribution. So I know that I want to convert this probability statement into 1 minus the probability that x is less than or equal to 69, because the CDF function only works for finding the values below a certain point, much like Table A. So in my calculator, I'll do 1 minus the binomial CDF. We're talking about 509 games. Probability of hitting a home run is 11.6, and we want to go up to and include 69. If you type that in your calculator, you're going to get 0.0764. And you can see that these two probabilities are close to one another. It's called the normal approximation for a reason. This one's actually a little bit more accurate, the one with the CDF function, but the normal rules do apply, and I need you to be aware of that. That wraps up everything we need to know about binomial distributions for now, and so you should be able to complete your homework assignment that was listed on Moodle for today.